Good morning. In this presentation, we are going to discuss a type 1 solid fuel problem. Here is the diagram with the given in black and the required and unknowns in red. First, we set a basis of 100 kilograms of coal. We then convert the mass to moles using each of the elements' atomic weight to obtain the kmoles of N and S in the fuel. Now, let's look at the composition of the DSG. Since we only have N4 as the unknown, we can obtain it by difference, giving us 79.21% nitrogen. Now, we get the moles of the dry stack gas using sulfur as our tie component. By performing S atomic balance, we have DSG, which is 55.83 kmoles. And using the mole percentages of each of the components in the DSG, we can obtain their number of kmoles. So, we can also get our N1 in the fuel by using C atomic balance, and this gives us 6.04 kmoles of C. Next, we can obtain our excess O2 by manipulating the formula of free O2. We already have the values for the equation, and so we have 4.625 kmoles of excess O2. Then, we can solve for our N2 in air by using this following equation, that the nitrogen in DSG is equal to the nitrogen in fuel and the air. And so this gives us 44.15 kmoles of nitrogen in air. And by using that value, we can obtain the O2 in air through the ratio. And so we have 11.74 kmoles of O2 in air. Next, we can solve for our TiO2 by subtracting the excess O2 from O2 in air. So we have 7.11 kmoles of TiO2, or the required oxygen for the complete combustion of the 100 kilogram coal. Finally, we have complete data to solve for our percent excess air. By plugging them into the formula, the percent excess air is equal to 65.05%. To start our complete ultimate analysis, we first look at this relationship, which is the total H in fuel is equal to the net H plus the H in combined water and moisture. So we solve first for the O2 unaccounted for, and substituting the known values, we have 0.79 kmoles O2. And through this reaction of combustion, we know that 1.58 kmoles of H2O is produced from combustion, that is by using the stoichiometric ratio. And we also note that the net H burned to H2O is 3.16 kmoles H. So we have the net H burned to water. Now let's look for our net H. The net H is equal to at net H burned to water plus H from the H2 in DSG. So 3.16 plus 0.32 times 2, we have 3.9 kmoles of H. Then, we can solve for our total H in the fuel by getting the H in combined water and moisture. But first, we want to know the combined water and moisture using the modified analysis, that is, by difference. So we have 3.12 combined water and moisture. But since that is still in water, we get the H in CW and M using this ratio 2/18. And so we have 0.35 kmoles of H in combined water and moisture. Adding that value to the net H that we have obtained earlier, we can get the total H in the fuel. So the total H in the fuel is 4.25 kmoles H. Next, by complete ultimate analysis, since O is the only unknown right here, we can obtain it by difference, giving 2.77%. Now we have a complete ultimate analysis. Thank you.